Josh Miller, who is a first-year PhD student at Imperial College and has been working on building interesting hardware platforms to tackle the lack of data in biodiversity. So, Josh, please take it away.
Thanks. Okay, so yeah, I'm going to talk about biodiversity monitoring, how we can go from sort of current approaches to getting more data at scale. All of what I'm going to talk about is relatively early work, so I'm keen to hear what people think and your suggestions. I'm not sure how these normally work, but happy for anyone to sort of jump in with questions at any point. So we need more data about our planet in order to meet our biodiversity goals. Our current understanding of biodiversity patterns and health and the impacts of climate, biodiversity, etc., it's all often highly dependent on sort of short-lived and localized data collection projects. So I think Sylvia is going to talk about citizen science approaches for collecting more data at scale. But I'm going to focus on slightly more traditional approaches for biodiversity monitoring using sensors and sensory networks. So there are loads of devices out there for biodiversity monitoring right now, and they can sort of be grouped into three kinds. So you've got devices like the audio moth, you can see it on the tree there. These devices are open source. The audio moth, I'm sure a lot of you have heard of. It's a great example of a really successful open source project. And it does low power and affordable acoustic monitoring. The problem with these sort of devices is they're usually only useful for one use, like acoustic monitoring. They don't sort of lack capabilities for integrating with other sensors, and often lack the compute for doing stuff like on-device machine learning. At the other end of the scale, you've got devices like the one on the right here. So these are commercially made, so often not open source, multi-sensor devices. These can provide really rich co-located data, but they're usually expensive and they're power hungry, and therefore they can't really be deployable at scale, especially given the typical budgets of most sort of conservation projects. So what most sort of field researchers end up doing, if they can't use a device like the audio moth for whatever question they're trying to answer, they end up having to custom build devices like this one in the middle here. And again, this is not feasible for doing at scale. The devices are nicely built and collect the data you need. But this device here, in particular, for example, it takes the research you built this a week to set and put together each unit. So it's just not really feasible. I have borrowed this from Eric, who did a seminar here a few weeks ago on partner-driven co-design for environmental sensors. I've just included this because I think it kind of highlights the area for optimization quite well. So this is the sensor life cycle. He conducted a number of interviews with various field practitioners and conservationists and looked at the ways in which they gather data. And he drew this up based on his findings. So it goes from the data need finding, where you identify what kind of data you need to answer whatever question you're looking at, all the way to data analysis. But the middle part in particular is what we're focused on. Researchers typically spend a long time on technology selection, designing custom-built sensors, iterating back and forth, testing, as well as on deciding how to effectively deploy and maintain sensors, which often involves designing further data pipelines and interfaces. So our goal is to build a low power and low cost device with multi-sensor integration, lots of nice power management features, battery health checking, etc., to really streamline this life cycle, as well as to collect, be able to collect more richer co-located data and allow for deeper analysis. Now, there's a number of challenges here with building such a device, from identifying common requirements across various use cases, so the device that remains generalizable, maintaining low cost and low power whilst having quality and power hungry sensors, as well as obviously building a product, with a casing and interface that is usable and rugged, but yet expandable. So yeah, I'm going to show you today our prototype, which is, like I said, very early stages, but kind of acts as a proof of concept of how a sort of multi-sensor device could work. Here's obviously the prototype itself and how it looks right now. We call it Terracorder. Any Star Trek fans in there? Yeah. So yeah, it's ESP32 based, specifically based on a variant of ESP32 called the Power Feather, which has a number of really nice power management features, a slow deep sleep current. Yeah, and it's got a 5-megapixel camera and PIR sensor for a motion activated camera. It's also got a microphone. Now we obviously plan on expanding this, having lots of open GPIO for further sensor integration, and have GPS and solar recharging and some means of communication via MBRT or LoRa for remote deployments. But this right now can sort of sufficient to look at what power consumption might look like in a real world deployment, because these sensors we've got, the cameras and the microphones, they are by far the most power hungry. This sort of all these nice hardware features are useless without some on-device scheduling for power management. So here the goal is really to assess what the power consumption of our device might look like in a deployment. And we use a number of fixed schedules. So essentially the device wakes up, it either records or doesn't record, then goes back into deep sleep for power saving. And we're looking at how we can schedule this. So we look at fixed schedules, the device wakes up at a fixed rate. But as well as this, we're also looking at using on-device reinforcement learning for adaptive scheduling. So this can enable dynamic adaptation to varying environmental conditions, which could potentially lead to greater power saving or like a nicer balance between power usage and event detection performance. This also has the sort of useful side effect of generating large-scale data for conservationists by learning the schedules of whatever is being monitored across varying environments. This could perhaps sort of answer questions on behavioral patterns in different environments. So we use Q-learning for our adaptive scheduling. This model-free reinforcement learning algorithm learns discrete state action values. So it means that lookup or inference is essentially a table-based lookup here, which makes it super lightweight, especially if you're using a highly discretized state. So we use time as our state here, time alone, plus a number of actions which correspond to sampling rates. So we discretize our time into hourly periods. We use 7 different sampling rates. So that's ranging from about 3 seconds wake up to about 30 minutes. This results in a 24/7 Q table, which is only about 3 kilobytes in size. You can fit a number of these on the device to schedule different components. And we use a reward based on a weighting of the positive activations, so the activations in which your device wakes up, detects an event, and the negative activations. So this essentially maximizes events detected at minimum power usage. But our reward it's easily adaptable to optimize for other constraints. So how do we
would you be able to give some examples of what would count as an event, like for the different sensors?
Yes, so we're going to focus on acoustic monitoring here for bird vocalization. We've got the motion activated camera, but then we're going to schedule the microphone.
Yeah, cool.
So yeah, so how do we model what this could look like in real world deployment? So we have got a load of event data. This is based on audio recordings from a device located here in the Sabah rainforest, Malaysia. Been there for some while now. And this device and its data is part of the SAFE project run by Sarah, that I think some of you may know. Yeah, we take sort of continuous audio recordings from this device and we process them with BirdNet, which is a bird vocalization detection model. And this can generate us essentially event timestamps and durations, which we can use to sort of simulate a real world environment. We also implement real-time event detection on the device. So the device has to wake up, obviously detect whether or not it believes there's an event occurring, then either continue to record or go back to sleep. So the usual approach for this is using Gödel filtering, which is like a digital filter based Fourier transform algorithm. So it can kind of detect if there's certain frequencies in an audio stream. The problem with this is it leads to lots of false positive detections. So we also implement a quantized convolutional neural network, which is trained on Mel spectrograms of bird death detections and non-detections. So we implement both of those on the device for evaluation, and both can process recordings at sufficient latency to enable real-time detection. So here's the various power measurements of the device's modes. This is recorded using a high voltage power monitor. So you can see we've got a really low deep sleep current, which obviously jumps up when you're recording or for camera activation, transmission, etc. We also have the overheads here for the Q-learning inference and update, as well as for the real-time event detection using the Gödel method or model inference for the CNN. Okay, so here's the results. The headline metric is we're seeing an estimated battery lifetime of over a year based on this real-world deployment data. So this is using a 13400 milliamp hour battery. The graph here shows the captured events versus battery lifetime for our Q-learning algorithm plus a number of other fixed schedules. But you see the Q-learning kind of strikes a balance. There's loads of room for optimization here with the Q networks, increased state action spaces, and some other optimizations I'll mention later. I say this is a conservative estimate because we don't use any solar or energy harvesting or any battery recharging methods here whatsoever either. So what comes next? We're going to look at essentially combining the rich multi-sensor data that we get from our device with multispectral imaging. And this could potentially enable us to build foundation models of biodiversity and climate patterns to perform measurement correction via data assimilation, as well as potentially tackle large-scale behavioral questions, especially for species which might communicate in multimodal ways. Other future work, we're looking at how these devices might operate in a network context. So this looks at a standalone device right now. This is often the case, devices are isolated, but having mesh networks of these devices can obviously enable opportunities for further optimization and power management. We also want to look at further optimizing the power management of individual devices by doing sort of voltage or multi-core scheduling. We want to look at the verifiability of our sensor readings. So this is massively important for biodiversity monitoring, especially if the monitoring is being done as part of a financial scheme. So, for example, a farmer could get a reward based on having high or improved levels of biodiversity on their farm, or it could sell their products for higher prices. So it's really important here to be able to verify that any recordings made by the device to assess the levels of biodiversity were actually made with tampered with device in the location where it's supposed to be, and that the recordings were natural and they weren't man-made effect. We want to look at using ML-based compression for efficient audio transmission, potentially even real-time audio transmission. This could use a kind of knowledge distillation-based approach where you have a quantized encoder on the device plus a larger decoder model up in the cloud. And obviously, we want to do loads of evaluation and iteration by real-world deployments, of which you've got a number lined up, including with Sylvia here looking at hedgehog monitoring. So yeah, here's a QR code for an archive preprint to about everything I've talked about in more detail. Like I said, it's obviously all relatively early work, so really keen to hear what people think and happy for questions. Thank you.
Now, are there any questions? Amelia, go ahead.
Sorry, so I had a question about comparing the fixed schedules to the like Q learning approach. In essence, so with the fixed schedules, I assume like when you're saying 3 seconds, it's not that it's waking up every 3 seconds, but that like every time it wakes up, it records for 3 seconds or something, right?
No, it's waking up every 3 seconds.
Oh, okay.
And yes, sampling for like a split second to detect whether or not events occur, and then
Okay.
either continues to record.
Okay, so all of them have the same fixed sampling length, but the schedule is so wake up every 3 seconds. Q learning algorithm just varies that, right?
Yeah, so
Essentially.
we're just using hourly periods here.
Mm.
So it basically learns for, you know, say 3 o'clock, it'll use a 3 second sampling, or for 7 o'clock it'll use.
Oh, okay, I see. And then, and these are like this reinforcement learning algorithm is being trained on device, so each device would be able to generate its own schedule based on
Yes,
like
that's the idea.
the local, whatever, the local like biodiversity patterns.
So you can deploy these devices in various contexts, and they'll learn the schedules of whatever's being
Yeah.
monitored for it to be deployed. Yeah.
Very, very cool, thank you.
I was wondering, how come the like captured events for 3 seconds is 100%? Is it because they're like relative, just in the like relative to that as the kind of, because surely if it's not capturing everything, if it's only waking every 3 seconds.
You know, I think basically all the sort of burn net detections ended up being longer than 3 seconds. So we just ended up capturing everything but for 3 seconds. Yeah.
And so tell me more about the devices themselves. Can you do cooperative scheduling, for example? Is there any way they can talk to each other to figure out which one should see these events?
Yeah, well, that's what we're going to look at for the network context essentially. And that involves how devices could perhaps wake up other devices based on, you know, movements of whatever being monitored, stuff like that. Yeah.
Oh, I have just one other question too, actually, about this. In terms of a baseline, the IO-moth or a off-the-shelf camera trap, how long is the expected battery, or what's the kind of average battery life of these things?
The audio-moth has a long battery life. They're quite good. You could probably deploy them for like well over a year if you use solar panel. But obviously they only do audio monitoring. These kind of the larger camera trap devices have much lower battery life.
So you need people to go out to the field to replace the battery and download the data every few months or so?
Yeah.
Are there any questions online?
I think Orlando posted something in the chat.
Oh, there we are. If I can find my. How do you, can anyone see the chat?
Yeah, if you click it again.
I am.
Apologies if I missed it. Do you
Oh.
consider changing patterns in events, example, seasonality?
Yeah, it's something we've got to look at in more detail. I mean, the idea is you put these devices out there and they learn in schedules, so obviously those schedules would evolve over time. But it's we haven't actually been able to assess how well these the model of the schedule evolves based on seasonality yet, because we just don't have enough data.
Perhaps thank you very much for the talk, it's really good. From more of a similar to what we're looking at perspective of kind of a systems, kind of how easy is it to get all of the kind of code that you need for these devices and all these bits of hardware and build that and put them onto these devices and then deploy them, and then maybe subsequently try and change the software that's running on any of these devices? Is that really hard, or yeah.
Well, we've used the ESP32 because it's quite well supported. They've got some nice SDKs and stuff for programming them, but yeah, it's not easy. I haven't actually even considered yet how you possibly update the code remotely and stuff like this. Maybe something for someone else to look at, but yeah, it's definitely something we got to think about. Yeah. Really thinking.
Now from Tiffany, so how long-term will these devices last, and do they fit well with earlier devices such as audio moths? Can they readily be swapped in places where there has been long-term monitoring already with these previous devices?
Yeah, well, hopefully these devices could last for, kind of as long as the projects they're being used for, really. I mean, the constraint now comes from the actual lifetime of the battery itself probably degrading. And maybe perhaps we should look at start to look towards batteryless devices and stuff like this. We actually use the exact microphone used by the audio moth with this device, so they should be pretty swappable, yeah.
Thank you, everyone. Sylvie, go ahead.
A very quick one, especially because my laptop is restarting. Classic, failed by technology. But we actually, in my previous job, we did something sort of similar in concept. We actually created a camera that could actually record sort of time-lapse images in tunnels under the roads to monitor amphibians actually crossing. And the really big complication there, which for me at the time was actually surprising, was because we needed an infrared flash. The big energy demanding spike was actually in making sure that when the image was captured, was actually exactly simultaneous with the flash. Mm-hmm. That ended up actually taking so much battery power that by the end, it was actually cheaper for the battery life to just emit this sort of continuous infrared flash all the time. Actually it operated kind of continuously because it was so difficult actually to sequence them. Yeah. I was wondering if you had anything sort of related to that, which for me was a big surprise. It didn't actually occur to me that it was going to be so energy demanding, sorry.
Yeah, I'm surprised here that was your biggest cost, really. But no, I've not looked at using infrared or anything yet, so
okay.
Exactly.
You might come to it.
These infrared cameras aren't really optimized for power usage. They don't typically operate with these kind of battery type environments. So yeah, we should probably scan each individual class of sensor separately, right? See what it looks for.
Yeah, because the obviously when you collect the image, it's such a small fraction of time that it needs that synchronization to be absolutely spot on.
Yeah.
And basically, actually, that meant that every time the flash was waking up, you kind of needed to track it exactly.
Very high frequency times.
Exactly.
Yeah, yeah. Brilliant. All right. In that case, let's thank you again.